Welcome to 67th lecture. We are studying circuit analysis and we are studying three-phase systems. In this lecture, we will solve an example where our delta connected source, it's a three-phase source, is driving our delta connected load. Right. The things that we are given is the S of the load. S means the complex power absorbed in the load is 1000 mega volt ampere. This is mega. Mega means 10 to the 6. And it is working at a power factor TF load 0.8 lagging. 0.8 lagging means this is an inductive load. Right. The line parameters are 0.1 plus J 0.2 ohms. This means a resistor of value 0.1 ohm in series with an inductor having inductive reactance 0.2 ohms. This box can be drawn, can also be drawn like this. A resistor in series with an inductor. The value is 0.1 ohm for the resistor, and this is the inductive reactance of the inductor in series is J 0.2 ohms. Right, so these are all ohms. Right, we are required, we are also given that the line voltage V, the magnitude of VAB or VBC or VCA is equal to the magnitude of VCA is given to be VCA is given to be 500 kilovolts. Kilo means 10 to the 3. We are required to find the line current IL, either IA or IB or IC, the magnitude of it, and the power dissipated in this line. We know this line has a resistive portion 0.1 ohm and inductive portion having inductive reactance equal to 0.2 ohms. Right. Let's solve this problem. The S, the complex power of load, we studied in last lecture, CA66. In this lecture, we studied that the complex power can be written as, in fact, the magnitude of complex power can be written as square root of 3 times the line voltage times the line current. This means the line current can also be written as the load, magnitude of S load divided by square root of 3 times V sub L. So we'll put the value of S load that we are given 1000 MVA. So this is 1000 megavolt amperes, right? Instead of mega, we write 10 to the 6. Square divided by square root of 3 times VL. VL is given to be 500 kilovolts. Kilo means 10 to the 3. So when we divide these two quantities, it comes out to be 1.15 kilo amperes or 1.15 multiplied by 10 to the 3 amperes. So this is the line, the magnitude of line current, either IA or IB or IC. This current or this current or this current. We know that the magnitude of these currents will be the same, but their angles are different. They are 120 degrees apart from each other. Right. The last thing that we are asked to compute is the active power or average power dissipated in the line. We know that power dissipated in line is the power dissipated in the resistor 0.1 ohm plus the power dissipated in the inductor having inductive reactance 0.2 ohms. In previous lectures, we have studied that active power or average power dissipation in inductors and capacitors is zero. So we have only active power dissipated in this 0.1 ohm resistor, and we know that the power dissipated in resistor is, we have multiple expressions for this. Either it can be V multiplied by I, or I squared multiplied by R, or V squared divided by R. So we will multiply I squared multiplied by R, and since these are line quantities, we will multiply this with square root of 3. We have already studied that for line quantities we have this square root of 3 multiplied in case of three-phase systems. And if these are phase quantities, we multiply, instead of square root of 3, we multiply with 3, right? So we multiply square root of 3 times I line. I line is this, we have just computed that, squared times the R line. R line is 0.1 ohms. So this comes out to be 0.4 megawatt, right? We will continue, that's all for this lecture, but in our next lectures we will continue studying three-phase systems. Thank you.